When I lift something, I do work. I put a force on it over a distance. And when I do something simple like lifting something against gravity, the force is constant. It's the weight of the ball. But what happens if I have a different kind of force? I'm storing a different kind of potential energy. An example of that would be like a rubber band. When I pull back on a rubber band, I'm actually using force. I'm doing work. I'm pulling back on it. But if you've ever pulled on a rubber band, you know that it's really easy to pull at the beginning, but harder to pull at the end. Same thing's true with a spring. If I put a spring here, if I put a weight, so I do a constant pull on the spring, it's going to displace itself a certain amount. The spring has a returning force that's equal to the weight that I put on it. And it moved a certain distance. It moved from here down to there. So I don't know, a couple of centimeters. A different spring, it's going to move a different amount. This one barely moves at all, move from here to there. That's because this string has a lot higher tension on it. It's a lot tougher spring. So we need a number that's going to talk to us about how much pull this spring has. As you pull back farther, the force is greater. That's different than gravity. When I lift something, the force is the same as I lift it higher. But here, as I pull back, the force gets greater. You actually create a force versus time graph. Let's take a look at those today. When I lift this ball, if I created a force versus distance graph, the force would be constant. So the farther distance that I go, the force would be the same. That's not true with a spring. The force versus time graph for a spring is going to actually be more like an angled line or a sloped line. Because as you get farther in distance, it requires more force. The slope of this line has to do with how tough the spring is. This one, that's not quite as tough, doesn't have as steep as a slope as this spring here. This is called the spring constant. And so we calculate the spring constant using an equation. And you can see that here. So as I pull back farther, the force gets bigger. What about the amount of energy that I do? If I look just at lifting this ball at a force versus distance graph, the energy would be force times distance. Well, on that graph, it's going to be the area under the graph. The same is true when you use a spring. As you pull a spring down, the force gets greater. So it's not a horizontal line, but the work that you do is still the area underneath the graph. We used to do a lab dealing with springs. We would put weight on here to figure out what the spring constant is by putting more and more weight. But I thought this year, let's do something a little bit cooler. Let's find some other kind of elastic potential that we can work with. I thought, why not use a bow? Okay, so here's the setup. I got my bow clamped to the table, and I'm going to start putting weights on the bottom here and measure the displacement of the weight to see how tough this bow actually is. That'll allow me to get the spring constant of the bow, and then I can actually figure out how much energy I put in the bow. Let's see how it works. I have a 1 kilogram hanger here. I'm going to put that on the bow, and you can see that, well, I'm going to lift it up so that the string isn't doing anything. And I'll find that it starts at 63. It starts at 63. But when I put the 1 kilogram on there, it's now down to about 64 and a half. I better check this really good. It's about 64. So with 1 kilogram, it has moved 1 centimeter. Let's put 2 more kilograms on there to see what it looks like with 3 kilograms. So with 3 kilograms, I'm down to about 69 centimeters. 4 kilograms. I gotta let her stop bouncing here. I'm down to 72. So from the original 63, I'm down to 72. Let's put 5 extra kilograms on there. So a total of 6 kilograms. I got this big heavy thing here. Put that on there. And I can see that I'm now down to around 80 centimeters. So from the 63 to the 80, that's a difference of 17 centimeters. I can start graphing this and see if I can't get the spring constant. I'll give you guys at home some data. If you're in class, you're going to actually do this with your own bow to see what your spring constant actually is. From that, we're going to calculate the amount of energy that we stored in the bow. Doing that, we can figure out how much energy, potential energy I stored. When I let go, that energy turns into kinetic of the arrow. We can actually find the speed that the arrow leaves the bow. I've never actually done this before, so I don't know how well it works, but I think it'd be cool if we then went outside, maybe to the football field, pointed this thing at 45 degrees and fired it. Given the amount of energy we put in, we should be able to calculate just about how far that arrow goes using the range equation if we know the speed that it leaves the bow. Let's give it a shot. Let's look at how far back I can pull this thing. So if I take my meter stick, set it here, you'll see that the string actually starts at about 22. And if I pull it back like I'm shooting an arrow, I'm ending about 67. So that, if I were to shoot an arrow, that's the amount of potential energy that I'm putting into the bow. Let's see if we can't figure out how fast this arrow is going to go. I measured the the weight of this arrow, the mass of this arrow, to be 28 grams. Let's see if we can't figure out how fast this thing's going to go. Okay, we're going to give this a shot. It's been a long time since I've done this, so we'll see what happens. The first one I'm going to try to shoot horizontally, and we can see if we can find the speed of the arrow as it's leaving the bow, and see how close it is compared to the one that we calculated with the energy. So trying to shoot horizontally. That went 35 yards. I'm going to attempt to shoot this at about a 45-degree angle and see if I can get it to go as far as I can. I don't have a protractor or anything. I'm just going to try to guess at what a 45-degree angle is. And we'll see if we can't get the way it works here. That landed, I don't know, I gotta go check. That landed about 80 yards.